types. And then that is the first step. So one of the important things we discussed in the last session is some of the more important points while considering meshing the model. The elements must be made small enough to give usable results and yet large enough to reduce the computational effort. So we need to make a balance between element size so that it should give usable results and also reduce the computational effort. That's how we need to make a balance. So there will be a lot of techniques will be there that we can discuss later, but we need to ensure that we use optimum element size so that we can get usable results as well as reduction in computational effort. And also another important point is we need to choose appropriate element type so that it will closely matches with the physical behavior. So the element types, various types of element types we do have, and which represents 1D model, 2D model, and 3D model. So we need to ensure that we choose an appropriate element type for the given problem. So these are the two important things we need to consider while doing FE modeling. This is the step one. So these things we already discussed. How the results converge from coarse mesh to fine mesh. There are three types of meshes used here with 0.5 mm size, 0.1 mm size, and 0.05 mm size. So if you see 0.1 mm size and 0.05 mm size, the stress magnitude remains same. Very minor variation is there. That means for this given problem, with each element, and function is defined using model values of the element. Now, there are different types of functions associated depends upon the element types used. They may be linear and quadratic polynomial functions. And basically this function is the displacement function is function of coordinates x, y, and z. So these are the important things. Maybe when we try to do some small example, we try to understand what is exactly this displacement function. And then we need to establish a relation between strain displacement and stress strain relationship. The reason is in finite element method, the key features is displacement. So from displacement to calculate strains, we need to establish a relation between strain and displacement. Once strains are calculated, again we need to calculate stresses. Again we need to establish stress-strain relationships. Okay? These are the 1D problem related relationships here. So once when we establish relationships, so we need to work on deriving stiffness matrix and equations. There are several methods involved here: direct equilibrium method, work energy methods, and methods of residuals. These are some of the methods available. So stiffness matrix and element equations related to nodal forces to nodal displacements are obtained using force equilibrium conditions at basic element along with the force and deformation relationship. So basically the stiffness matrix is related to nodal forces to the nodal displacement. As you see, like if stiffness is force upon unit deformation. Okay, so it's a direct relationship between the force and deformation. Okay, a simple technique, direct equilibrium method, is a simple technique to establish the stiffness matrix equation. Then we have other methods like work or energy methods. These methods, the direct equilibrium method is usually especially useful only for 1D problems, whereas for 2D problems, you need to go for work or energy methods. So there is we have principle of virtual work, principle of minimum potential energy, Castigliano's theorem, are the methods used for this type of work or energy. And there is a third thing is a method of weight research. These are like similar to energy methods. So these are the methods which we use to develop the stiffness matrix. So when you try to write force stiffness and deflection, it looks like this. Okay, this is a force matrix, this is stiffness matrix, and this is the deformation matrix. Okay. So once we establish the stiffness matrix, we need to ensure that all these matrices are assembled into global matrix. So global stiffness, because we derived only for one particular element, there are n number of elements. So we need to try to assemble all these stiffness matrices into one global. So each element will have one stiffness matrix. So at the end, like when you try to assemble, when you try to get a global stiffness matrix, you have to assemble all these global stiffness matrix into global stiffness matrix. So one of the important aspects is global stiffness matrix is singular matrix. When you try to calculate that value, so when you try to inverse stiffness matrix, it will be non-existent because the determinant is 0. So the structure will be unstable. So boundary conditions must be applied for the given model so that the singularity in the stiffness matrix will be avoided. So if you try to see any mechanical problems, anything in general in physics, any component or anything will be having a boundary conditions. If the boundary conditions are not there, then it will be unstable. Okay. So similarly, in theoretical aspects of finite element method, when stiffness is singular, that means when you try to make it inverse, it will be non-existent, resulting in the unstable conditions. Okay. To avoid that, we need to give boundary conditions. Then only these equations can be solved. So this we will try to understand small example which I will be discussing in the coming slides. Then you will appreciate this thing. So this is the global assembly equations. So these equations can be solved for displacement by using elimination methods like Gauss method or Gauss-Seidel method. So displacements are the primary unknowns because they are the first quantities, as I mentioned earlier. Displacements are primary unknowns and they are the first quantities determined using this method. So once the displacements are calculated using relations between relations, displacement strains are calculated and then stresses are calculated using these equations are valid only for one dimensional problem. So there will be relations established for 2D and 3D as well. So we need to use those equations. And then final step is like if you interpret whatever results we achieve, whether those results are making sense or not. Okay. So let us take a small example. This is a one-dimensional spring, okay, and it is pulled by tensile forces T in either directions. Okay. F1x and F2x are local nodal forces of the spring at one. This is one element, spring element, and this is node 1 and node 2. So node 1 and node 2, and F1x and F2x are local nodal forces on the spring element. So at node 1 force will be F1x, at node 2 force will be F2x. Similarly, D1x and D2x are the nodal displacements. D1x displacement at this location, D2x at displacement at this location. So from our earlier equation, if you try to put the force, stiffness and deflection equation equals to K into D. So this is the relation of this is the force matrix, this is the stiffness matrix, this is the displacement. Okay. So our first step is discrete and select the element types. So we have selected an element, one dimensional spring element, and we try to put a material property. We have taken K as a spring constant. Okay. Then we have to select a displacement function. Okay. So displacement function we have selected U equals to A1 plus A2x. Okay. So this will be varying across the element this way. Okay. So basically here you need to understand using this function we can interpolate stresses across the element thickness. Okay, across the element level. So this function we have assumed. Okay. So now coming to putting the constraints. Okay. What are known values at x equals to 0? We are having d1x displacement. X equals to L. We have d2x displacement. So if you try to put those equations here, okay, at x equals to 0, we have a1 is nothing but d1x. At x equals to L, we have from there we can calculate a2 here, d2x minus d1x by L. Okay. So now we need to establish stress strain or stress displacement to stress strain relationship. Okay. So when we try to pull tension spring in either in two directions, okay, equal and opposite, because we are pulling at this node this way, and we are pulling spring this way. Okay. And where the delta will be calculated just minus d1x, but here actually we are showing d1x in positive direction, but when you try to apply tension force opposite direction, then d1x become negative direction, negative values. Okay. So we calculated the delta as d2x minus d1x. Then when you try to put force deformation relationship, so force in the spring is nothing but K into delta. Delta is total deformation. So that is written as T equals to K into d2x minus d1x. So by the sign convention of the nodal forces, we have at F1x, so we are pulling opposite direction on x-axis, so it will be positive E. Okay. So then we can then T equals to minus F1x K into d2x minus d1x. Similarly, T2 equals to K into d2x minus d1x. So when you try to rearrange these equations, so K is common and it's d1x minus d2x. F2 equals to K into d2x minus d1x. So when you try to put in matrix form, then it will be F1x, F2x. Then we can take d1x and d2x side, and then we can put all the stiffnesses here. Then it will be K minus K minus K and K. So this is the local stiffness matrix of a spring element. This is how we derive. So So any questions here? Just it's very important. If you have any questions, we can have a discussion. It's very important for you people to understand this stiffness matrix. So just let me know if you have any questions. We can have a discussion. Otherwise, I'll continue. Now let us take one small example. Okay. I have considered two springs here. This is one spring and this is the second spring. And they have stiffness K1 and K2. Okay. So x-axis is the global axis. The local x-axis of each and coincides with the global axis. So these are some of the things. So let us try to work on this example. So let us understand how we can assemble it. So for element 1, okay, F1x, element 1, we have two nodes, node 1, node 3. So F1x, F3x equals to K1 minus K1 minus K1, K1. This one we have derived here. Then D1x is displacement at this location, and D3x is displacement at this location. Okay. Similarly, for element 2, we have F3x and F2x forces equals to minus K2. K2 is the spring constant of this spring, minus K2 K2 into D3x displacement at this location and displacement at this location. So these are the two stiffness matrix and problem. So we need to try to understand how to assemble this. So some of the important thing we need to ensure that element 1 and 2 are connected at common node 3. So for the continuity and compatibility requirements, we have mentioned D3x here and D3x here. Okay. So for compatibility and continuity requirements, this displacement at this node is same in these two equations. So D3x on first element, D3x of second element are same. Okay. So that we need to consider here. Okay. Now coming to more of understanding these forces here, how forces we can club it here. So at node 1, so F1x is nothing but whatever we have considered force coming from node 1. Similarly, F2x is nothing but nodal at node 2, F2x of 2. But F3x is summation of nodes load coming from element 1 and load coming from element 2. So this is to understand the forces acting in the spring. Okay. So now let us take all these three equations and try to put it into matrix form or try to assemble it. Okay. So we have this force and stiffness matrix here, force displacement stiffness matrix, and we have forces here. When you try to put this when you try to put these forces in stiffness and 3x of element 1 plus F3x of element 2. Okay, so F3x of element 1 is nothing but so if you see this is element 1 matrix, so F3x equals to K1 minus K1 into D1x plus K1 into D3x. So same thing is substituted here. Okay, d1x is nothing but d1x and d3x is nothing but d3x. That's what we mentioned here. Plus f3x of 2. f3x of 2 is here. So that is coming as k2 d3x minus k2 d2x. That is what mentioned here. Similarly, f2x is nothing but f2x of 2. So here directly we can take as k2 into d3x plus k2 into d2x. Okay, then f1x. f1x is nothing but k1 into d1x minus k1 into d3x. So everything we have we put into three different equations. So here d1x is nothing but d1x of element 1 is nothing but d1x, d2x of element 2 is nothing but d2x, d3x of element 1 is equals to d3x of element 2 equals to d3x. This is what we discussed in the last slide. So these are the equations we got it. Okay, after taking into account of forces in the model. Then if you try to put it to matrix form, okay, so directly we can put f3x, f2x, f1x, and we can put d3x, d2x, d1x. Then so d1x, we are having only d1x, one coefficient here, that is minus d1. Oh, okay, this is f3x, right? No, okay, f3, so we have d1x here, k1, then k1 here plus d3x, we have two factors here, k1 plus k2, that we have mentioned here. Then d2x we are having only one, that is minus k2, that we have put here, and d1x we have only one here, minus k1. Similarly, f2x we can be written as, so minus k2, d3x have minus k2, and d2x has k2, and there is no factor for d1, that is 0. Similarly, for d3x we have minus k1, that's what we are writing here. Then no d2, 0, and d1 we have k1, that we have written. So this is the matrix form as global stiffness. If you rewrite it to f1x, f2x, f3x, it's like this: k1 0 minus k1 0, k2 minus k2 minus k1 minus k2, k1 plus k2. So this is the global stiffness matrix for this given problem. It's a very small problem, and so again, this above equation can be written in matrix form, single matrix form. F is a global nodal force matrix, A is a global nodal displacement matrix, and D is global nodal displacement matrix, K is a global stiffness matrix. So this is the global stiffness matrix for this problem. So that is one method. Whatever I discussed is one method. We can do other simplified methods, like these are the local stiffness matrix for the given for the given problem. So here, okay. So we can write d1x, d3x, d1x and d3x and d3x, d2x. Like this we can write it, and we try to assemble. Okay. So what we can do is we can put d1x, d2x, d3x here, and we try to fill it. Okay. We can expand this matrix into much bigger way. Okay. So here we don't have d2x, right? So, but we have put d2x. But here k1 we take it out, and here we have k1 is there, so we can put 1 here. There is no d2x factor, so we can put d2x is 0, minus 1 for d3, because we are having minus k1, and we don't have any factor related to d2, so we can put all zeros here. Okay. And then here we can put minus k1 for d3x value, and here we d2x, no d2x, so we can put 0, and then we can put one here.
So we are having
So this is for this matrix. Similarly, for this matrix, we can rewrite it as like this, okay? Because we don't have A1 here, D1 here. So all the cells related to D1, we can make it
almost 10 days
and we can assign 1 minus 1 minus 1 1 here. D2 for D2 D3 we can directly assign. We can take D2 out and we can assign 1 minus 1 minus 1 1. And then we can sum it up, both the things. Now we can sum it up. I'm going to try to sum it up. It looks like this. So this is a global stiffness matrix. We are trying to sum it up. D1x, D2x, D3x into stiffness. And this.
So what we can do is, so when we are giving the structure on the tape, okay. So what I do is already I tell to Ramakrishna to create original passport. So we give the live demo and there itself we'll give its content details to all the students. So they'll see the demo, then they'll show the interest and automatically they themselves they go and they take the that will be also. Yes. So yeah. So this what you do is okay. For your mail ID and your which number you are going to use? Mobile. This number only. So what you do is for whatever number and email ID you want, so only those things are message. The same thing is forward. అది ఆగిందా
లేదు సార్ అట్లా చూస్తున్నా సార్ అక్కడ వాయిస్ అయితే అయింది కానీ మాస్తో మూవ్ చేస్తున్నాం సార్ పేజెస్
Things completely. That means on end it cannot move. That is the displacement is completely limited.
Tension ఉంటుంది.
So here in this condition, here displacements are
Modifications అవి చేసుకుని
arrested. That means
ఒకసారి సీసీ కూడా చూపించాను.
this part
సిక్స్ గ్రాఫ్ సైడ్ తీశారు కదా, కొన్ని చోట్ల నేను ఎక్సాక్ట్గా రిప్రజెంట్ చేయాలి డైన్గా.
this is called as
ఒక గ్రాఫ్ దగ్గర ఎట్లా
whereas
రెడీ
non-homogeneous
అది నేను
boundary condition. Instead of giving zero as a condition, we will give a specific value.
అది అయితే అలా మనం
Instead of considering it here, we will tell that this will be reflected to so many
కాదంటే
so many
ఇది
This
ఫీచర్ చేయలేదు.
is the non-homogeneous model. Homogeneous will be completely arrested and displacement will be zero. Non-homogeneous will be telling that instead of zero, some value it will be deflected to particular value. Okay, let us take this problem.
మోటివేషన్ చెప్పారు.
So in this problem,
సారీ కూర్చొని ఉండాలి.
so here we are arresting the spring at node 1. We are applying load at node 3, and also we are applying load at node 2. Okay. So here we are constraining, right? So what we are telling is D1 displacement at this node is 0. We mentioned here. Okay.
అది వర్తమానం గురించి అది మనం ఏం తెలియదు. అది అలా
So
జరుగుతుంది.
the above equations can be written as
మనోడు డబ్బు తక్కువలేపారు అందరూ. ఏం మాట్లాడదు స్టూడెంట్ మాట్లాడుతూ టెన్షన్ ఎందుకు? ఆయన ఆఖరికి రామగారు కాక మంచిదా చెప్పు, టెన్షన్ ఎందుకంటే
okay. So
అసలు ఒక గ్రాఫ్ లో ఎక్స్ యాక్సిస్ వై
so right now only is this equation and this equation.
అది రాసుకోలేదు.
It will come as 8.
2 గంటలు గైడ్ దగ్గర చెప్పడం కాదు, అక్కడ 10 నిమిషాలు
నా దగ్గర చెప్పమన్నాను, నేను చెప్తానని చెప్పి ఎస్కేప్ అయిపోయింది. నేనంటే పిన్ పాయింట్ తిట్టేస్తాను. లేకపోతే మనకి ఇలాంటి కూర్చుంటాం కదా, అడిగే ఫస్ట్ అయ్యే రిజల్ట్. నేను ఫస్ట్ నుండి మొత్తుకుంది అదే, ఎవరికైనా కావాల్సింది నువ్వు ఏ ఆల్గరిథం వాడో, నువ్వు చేసిన ఎక్స్పెరిమెంట్, నీ రిజల్ట్, దాన్ని ఎక్స్ప్లెయిన్ చేయడం అంతే, ఇంకేం అక్కర్లేదు. ఆ పాయింట్స్ ఎక్కడ మాట్లాడలేదు. ప్రతి చాప్టర్ 4 చాప్టర్స్ ఎక్కింగ్ పెట్టి ఇది ఈ మోడల్, ఇది చేశాను, ఇది రిజల్ట్ వచ్చింది, ఇది గ్రాఫ్, దీని నుండి దీన్ని డెరైవ్ చేశాను, అంతే కావాలి.
సబ్మిషన్ చేసి సబ్మిషన్ కరెక్ట్గా చేసుకుని సబ్మిట్ చేసి ఎవరికి రెడీ
ఏం లేదు, మా బుక్ బాగుంది, కాకపోతే ఏంటంటే రైట్ అప్ బాగాలేదు. రీరైట్ చేయాలి, ప్లస్ పిన్ పాయింట్గా రిజల్ట్ తెలియాలి. నేను చెప్పాను కదా, ఇప్పుడు సినాప్సిస్ చూస్తే మొత్తం బుక్ అర్థమైపోవాలి. చాలా ఎక్కడితో వస్తా ట్రై చేశాను.
మంచిగా ఉంది.
నేను మళ్ళీ లీవ్ పైన స్నాక్స్ అలాగే దగ్గరలో ఏమో అట్లున్నాయా?
దగ్గరలో వచ్చారు అందరూ
పర్లేదు, ఏదో ఒకటి దగ్గరేనా? ఎందుకంటే నేను 1 లోపు వెళ్ళిపోయాను అనుకో, సీఎల్ పెట్టకండి, లేదా నేను సీఎల్ పెట్టి ఇంటికి వెళ్ళిపోను. అలాగే వాళ్ళు నా కారు
లేదు.
లేదంటే ఇంకా వాళ్ళు మినిమం అంతా
రెడీ
the alternative method used to derive element equations in strictest matrix of an element. So this method is advantage being more general than method in which involves nodal and elemental equilibrium equations along with the stress strain law for the element. So one of the best alternative method for the one of the lectures earlier we have discussed. So it's this method is used basically to derive element equations and stiffness matrices. So one of the things is it is an advantage of being more general than method given which nodal and element equilibrium equations allow stress strain for the element. This method is applicable for elastic. So let us understand more on this principal energy, minimum potential energy. Okay. So potential energy of stress is generally expressed in terms of displacement. Okay. So d1, d2 are the displacements of in the structure. The total potential energy is defined as the sum of internal strain energy plus potential energy of the external forces. So one factor is coming from internal strain energy, and another factor is coming from potential energy from external forces. So this is the total potential energy. One is internal energy, one is strain energy, one is potential energy coming from external forces. So the strain energy is the capacity of internal forces. So the forces to do the work through deformation in the structure. And the external forces are the body forces, surface traction forces, and applied nodal forces to do the work through deformation of the structure. So these two forces are defined. One is external forces are the so for any body can subjected to various types of forces, namely like body forces, surface traction forces, or the inertial loads, whatever it may be. So these forces are make sure that it will do the work to the deformation of the structure. And so to minimize the potential energy, we need to differentiate with the deformation. Okay, not deflection. That means if you see this is the potential energy versus deflection or deflection. Okay, so if you want to get the minimum potential energy, this is the so we have potential energy function with respect to deflection. So if we want to get this minimum value, so we need to, as we studied in theory, differentiate with respect to. I think it's not visible. So when I try to draw potential energy versus deflection or deformation, So the minimum potential energy is happening at this point, at this deflection. Okay. This can be achieved only if you suppose this is the function, the potential energy. Then we can get this point by differentiating this function with respect to the displacement. So okay. So this is what we need to do. We need to differentiate with respect to the motions. So let us understand simple string problem. Same string problem. So first we need to identify what is the internal energy, internal strain energy, what is the total, what is the potential energy caused by external force. There are two things here, right? So first let us calculate what is strain energy. Strain energy from so one of the potential energy of the external force is being opposite strain instead from the external work action, because potential energy of the external force is lost when work is done by external force. So we need to account it as a minus of x. Okay. Then strain energy is calculated as for this thing half into k force into x. Okay. So we need to account if you draw force and deflection curve, it is a simple straight line. Okay. This slope will give stiffness of the spring, and the area under this slope will give strain energy. So we calculate strain energy. So when you try to put the total potential energy, it comes like this: half kx square minus fx. Okay. So this is the total potential energy. So using the above equation, the total potential energy can be written as. So the total deflection can be given as d2x minus d1x. Okay. d1x is deflection at node 1, d2x is deflection at node 2. So this is x can be written as d2x minus d1 whole square. Here fx is minus f1x into d1x, displacement at node 1, minus f2x. There are two external forces, f1x and f2x. So one force is given like this, and one force is given like this, and another force f2x into 2x. So this total equations look like this. Okay. This is the total potential energy equation. Now let us minimize this potential energy. So when you try to differentiate and equate it to 0, then it looks like k into minus d2x. When you try to differentiate and equate to 0, this equation is simplified to k into minus d2x plus k1 plus d1x equals to f1x, k into d2x minus d1x equals to f2x. Okay. Now if you try to write it in matrix form, now again we got the string okay into the displacement equals to but this is how we can derive for stiffness matrix potential minimum potential energy. Now let us solve one example. It's a bit complicated, but let us solve it. So there are total four strings here. Spring 1, spring 2, spring 3, and spring 4. And these springs loads are constrained at this location at node 5 and constrained at node 4, and two forces are applied at node 1 and node 3. Okay. So the total potential energy in the system is given there. So there are forces 1, there are four strings, right? Four strings. Strain energy equation is given for four strings, and there are five nodal locations separated to forces. So F3 is here, F4 and F5. So here we should not confuse between delta 1 and D1. Delta 1, delta 2, delta 3, delta 4 are deflections in string strings, whereas D1, D2, D3, D4, D5 are nodal displacements. We should not confuse between string deflections and nodal displacements. Nodal displacements are displacement at node at particular point, whereas string deflections are net effect to overall elongation in the string. The string will be having two points, two endpoints. So two endpoints have two deflections. So we should understand that total deflection will be the difference between the two end deflections. So delta 1 represents string deflection, D1 represents nodal displacement. We should not confuse between that. Now delta 1, we have given the relations between deflections, nodal deflections versus string deflection, as mentioned here. And when you try to substitute these equations here, the total potential energy equation, and integrating with respect to displacements, this is the total potential energy equation in terms of deflections, nodal deflections, after substituting string deflections as a nodal deflection, and then integrating with respect to each five deflections, D1, D2, D3, D4, D5. So this is how when you try to integrate this differentiate with respect to deflections at each node. We got almost five equations. So when you try to put together everything and matrix form, so it comes like this. This is the global stiffness matrix and global deflection. So global deflection represents all five locations. Global forces, all five locations. Now let us see. Let us solve this problem. We got the equation. Okay. Global stiffness matrix, global deflection, global forces. Now let us solve. Okay. We have D5 and D4 as 0. We have constraint vector and the node location 4. Those two things are 0. That means these two things are 0. And we have node location 2. Also forces are 0. There are no forces separated. Okay, 0. Then if you knock it off all the 0 things here, the reason is here we have 0. When you try to multiply this with this one 0, 0. So when you try to knock it off all those things, we have zeros here. Then you get a simplified equation. Three-dimensional matrix, no, unknown, and known. Okay. So here we can inverse this matrix, and we can get the. So we have F1 values and F3 values. And we know this stiffness values. So when you try to reverse it, we can get D1, D2, D3. So this is the new potential energy for simple problem. Similarly, I think we will discuss in next session on 3D problem for minimum potential energy. So before that, I advise you people to look into these aspects. Okay, in various textbooks, therapy, or and try to understand all these basics of containment. So any questions, just let me know for today's session. So somebody asked me sharing the material. So we need to follow some procedures here. So maybe like I try to ensure that we will get the files. So what I'll do, I'll pass to our L&D team, learning and development team. So they will in turn pass to your team, your coordinators. So give me a couple of days time. Maybe by Thursday I'll try to push some of the material what I have discussed with you, so that you can refer. Any other questions? I appreciate if you guys can answer the questions, then I understand, so that we can add more value to these sessions. No questions? So again, somebody is asking about mail group PPT. So I cannot share these presentations. The reason we have our own restrictions, it has to go through proper channel. So our related team will share all these materials. So maybe by today or tomorrow, I'll try to push some of the materials to your coordinators. They will share with you. So till that time, please wait. Okay. Okay, if you don't have questions, then we'll call up today. So we'll meet again on Thursday and we'll have a detailed discussion. Thank you.